Coulomb's law. So first of all, Coulomb's law is a experimental law. It has been observed that when two charged particles are kept a certain distance, there is a force between the two charged particles. So Coulomb has defined how much force is acting between the charged particle and what are the factors on which the force depends. So and the Coulomb's law is, we can say Coulomb's law is the experimental law as well as it depends or it is based on only point charge particle. So according to Coulomb's law, if two charged particles, let charge Q1 and Q2 are kept at a certain distance, R1, two charged particles Q1 and Q2 are kept at a certain distance R, then the force between the charged particle is directly proportional to the product of their charges and inversely proportional to the square of distance between the two charged particles. So we can write F is proportional to Q1 Q2 by R square. Now here proportionality sign can be replaced by a constant, and that constant depends on the medium between the two charged particles. So for vacuum as a medium between two charges, then F written as 1 by 4 pi epsilon naught Q1 Q2 by R square, and this term 1 by 4 pi epsilon naught is a constant that depends on the medium, it means space between the two charges. So 1 by 4 pi epsilon naught is a proportionality constant of vacuum. And its value is given as 9 into 10 power 9 Newton meter square by Coulomb square, where epsilon naught is the new term which we have introduced here. Epsilon naught is called electrical permittivity of free space. Electrical permittivity of free space, and its value is 8.85 into 10 power minus 12 Coulomb square by Newton meter square. So what is the meaning, physical significance of epsilon naught? As the name electrical permittivity, we can say just this word has come from the permission or permit. How the medium is permitting electrical field. It means whatever the electrical field produced by one charged particle, so what is the effect of that field on the surrounding medium, the factor which determines that factor is called epsilon naught or electrical permittivity. So the value of epsilon naught for vacuum is given as 8.85 10 power minus 12 Coulomb per Newton meter square. Now this is for vacuum. Similarly, if any medium is there between the two charges, now if a medium is between the two charges, then we can say force in a medium. Here we can write force in a vacuum or in a free space. The force in a medium, in place of epsilon naught, we will write the electrical permittivity of medium, and the symbol we will use only epsilon. So 1 by 4 pi epsilon Q1 Q2 by R square. So here epsilon is the electrical permittivity of medium. Electrical permittivity of medium, and that depends on as medium changes. So there is a certain relation between the electrical permittivity, there is a factor, or we can say normally electrical permittivity of a medium we are determining or we are writing in terms of or by considering vacuum as a reference. So electrical permittivity of a medium can be written as K times epsilon naught, where K is a factor by which we can say electrical permittivity of a medium is more or less than the vacuum. K is a ratio of electrical permittivity of medium, electrical permittivity of medium to vacuum, or it is also known as dielectric constant. Dielectric constant. So dielectric constant means, now from here we can write dielectric constant K is nothing epsilon by epsilon naught. This is the important relation. It means this is the ratio of electrical permittivity of medium to the vacuum. So in this term, F in a medium can be written as 1 by 4 pi epsilon naught into K Q1 Q2 by R square, and the value of K lie between 1 to infinity. K is equal to 1 for vacuum and K is infinity for metals or conductors. So value of K lie between 1 to infinity. K is K for vacuum or free space and K is infinity for metals or conductor. So from F is of medium 1 by 4 pi epsilon naught K Q1 Q2 by R square, and F in vacuum 1 by 4 pi epsilon naught Q1 Q2 by R square. So we can say F in a medium is equal to your F in vacuum by K times. Okay. Now see the certain properties of this force. Properties of Coulomb force. First point, Q1, Q2 are the two charges which are kept at distance r, and this is called the line joining two charges. This can be said line joining two charges. So first point we can say the same type of charge same type of charge body repel each other, while a positively charged body attract each other. Same type of charge body repel each other, while a positively charged body attract each other. Second point, the direction of force between the charges will be always along the line joining two charges. It means these are the two charged particles. These are two charged particles. So when we are talking about the direction, so this is the line joining the two charged particles. So direction of force will be always along the line joining these two charges. It means if these two are the positively charged particle, so force of repulsion will be there. Force of repulsion means force on the plus q will be in this direction and force on the plus q2 in this direction. It means those forces R will be in the direction along the line joining two charges. Similarly, suppose one of the charge is negative. Let this q1 charge your minus q1 and q2 charge let plus q2. Then also the force between these two will be along the line joining the two charges. It means one is the negative charge, another positive. So force of attraction will be there. Force of attraction means minus q1 force applied by the q2 in this direction, plus q2 force applied by the minus q1 in this direction. So direction of force will be always along the line joining two charges, either force of attraction or force of repulsion. So second point we can write direction of force will be always direction of force will be always along the line joining two charges. Okay. Now third point, Coulomb force is conservative force. Coulomb force is conservative force. So Coulomb force is conservative force means whenever we are talking about the conservative force. So conservative force, what is the meaning of conservative force? Actually, we are going to discuss what is the outcome of conservative force. The outcome of conservative force is that if any particle or any body is moving only under conservative force, so in a one cycle or in a one round means starting point and end point are the same. It means, for example, this is a body and this body is moving in any path, and this path, when it is moving under any path, and that path is cyclic path. Cyclic path means starting point and the end point are same. So if the body is moving only under conservative force, so the work done by that force will be always 0. It means the Coulomb force is conservative force. It means it has been found that if any particle has been displace or move in a cyclic path under this force. So work done has come 0. So from that we are defining Coulomb force is conservative force, or we can say in other way is that, or we can say the work done by Coulomb force is a point function, or work done by Coulomb force is point function. Point function means it depends on only initial and final position of the particle. It does not depend on the path followed by the particle. Next point, it follows the principle of superposition. It follows the principle of superposition. We can say F is equal to F1 plus F2 plus F3 and so on. What is the meaning of this statement? Coulomb force follows the principle of superposition. So what is the meaning of this statement? The meaning is that whenever more than suppose two charges are there, and we want to calculate the force on any one of the charge. So meaning of this statement is that the force between any two charge particle does not depend on the presence of other charge particle. It means let for example, suppose this is a charge Q, this is Q1, this is Q2, this is Q3, like this. Number of charge particles are there, and the distance between Q and Q1 we can say R1, Q and Q2 we can say R2, Q and Q3 we can say let R3. Now, if we want to calculate the force on charge Q, so force on charge Q does not, due to the Q1 does not depends on the presence of Q2 and Q3. And so force between Q and Q1 will be along the line joining the two charges, as well as magnitude is also given by the Coulomb formula. So we can say force on Q due to Q1 is in this direction if all are positive, F1. Similarly, force on Q due to Q2 does not depend on the presence of other charges. Either those are present or not present, the direction of force between Q and Q2 as well as the magnitude of force between Q and Q2 will remain same. So force on Q due to Q2 in this side, F2. Similarly, when we are talking about the force between Q and Q3, so that will be also in this way. So we can say now there are three forces acting on a charge Q, F1, F2 and F3. So net force on charge Q is nothing, it is the vector addition of the force produced by individual charge particle. This is the meaning of principle of superposition, and this is very, very important and very useful. We will discuss so many problems in which knowingly as well as unknowingly we are following the principle of superposition. This is very, very important. Now, next point we can say Coulomb force is an action reaction force. Okay? Coulomb force is action reaction force. Action reaction force. Coulomb force is action reaction force. Meaning of this statement? Meaning of this statement is that suppose we are having action reaction means we can say F12 plus F21 equal to 0, or F12 of minus of F21. It means when two forces are acting in the opposite direction and the resultant is 0, then it can be said as acceleration force. See, let this is charge Q1, this is your Q2. Two charges are there and both are if positively charged. So force on Q1 due to Q2, as both are positively charged, same type of charge, force of repulsion will be there. The force on Q1 due to Q2 in this side, the F12, the force on 1 due to 2. Similarly, Q2, force on Q2 charge due to Q1, the force on 2 due to 1, like this. And since the force depends on product of both the charges, distance between the charges, so magnitude of F12 and F21 are same. The magnitude of F12 and F21 same. So but directions are opposite. Then we can say F12 is equal to of F minus of F21, and that gives, this is your nothing, action reaction forces. It means whatever the force acting on one of the charge, same amount of force acting on the another charge, but in opposite direction. So these are the main properties of Coulomb force, and some more point we can discuss which can help us in solving the problem. See, Coulomb force in vector form. Coulomb force in vector form. Now see how we can represent Coulomb force in vector form. This is our coordinate system, and Q1 and Q2 are the two charges are present, and the position vector of charge Q1 is let R1 and position vector of charge Q2 is let R2. Now, line joining these two charges is this. This we can say R, modulus R. The modulus R means here R12 is equal to your R21 is nothing, modulus R. So R12 means position of charge 1 with respect to 2, and R21 means position of vector 2 with respect to 1, and this is the origin. Now, force on charge Q1 in this direction, that we can say F12, and force on charge 2 in this direction F21. So see, when we want to write force on charge 1 due to 2, force on charge 1 due to 2, so force can have two terms. One is the magnitude, another is the direction. So magnitude, directly we can say it is nothing by Coulomb's law, 1 by 4 pi epsilon naught Q1 Q2 by mod R. Mod R is square. This is the magnitude. And now when we are talking about direction of force on 1 due to 2 in this side, this is the direction of position vector of charge 1 with respect to 2, or R12 cap. Cap indicate means unit vector. The unit vector is nothing, it is your, so this is written like this, and unit vector is nothing, the vector divided by its modulus. So F12 can be written as 1 by 4 pi epsilon naught Q1 Q2 by mod of r12 whole cube into r12. This is the vector representation of force on charge 1 due to charge 2. Similarly, we can write force on vector 2, force on charge 2 due to 1 by 4 pi epsilon naught q1 q2 by r21 whole cube r21 vector. So, from above these two relation, we can write F12 is equal to your minus of F21, and that give you the same idea as we have discussed. These two forces are action reaction force. That give you the derivation also for action reaction force, and in vector form we can write like this. So, this is the another point, 6th point we can say, or we can say the Coulomb's force in vector form, how to represent the force in a vector form. Next point, the force between charges. When medium between the charges are partially filled, when space between charges are partially filled with different medium, okay, it means the whole space between the two charges is not filled with a single medium, number of or multiple mediums are there. Then how to determine the force between the charges? See, so the purpose or meaning of this point is, suppose Q1 and Q2 are the two charges and separation between these two are R, but the space between the two charges are filled with a certain medium, and that medium is not completely filled the space. That medium partially filled the space. Let distance between the two charges is R, but we have filled a medium with only T and the dielectric constant of the medium K. Now, how to calculate the force between the two charges? See, in that case, just remember the previous formula in which we have derived when the force is acting between the two charges in vacuum and in medium. So, what we observe, the force in a vacuum is given as 1 by 4 pi epsilon naught Q1 Q2 by R square. And now, force in a medium, suppose the same spacing between the charges is same, then how much force in a medium? Q1 Q2 by R square. It means two charges are there, and when these are in a vacuum, then the force is this, and when these are in a medium, then force is this. So, what we found, force in a medium is your less as compared to force in a vacuum. Then what to do? If we want to make a same force between the two charges, then how we can make the same force? It means magnitude of the force is same. Then if we are decreasing the distance between the two charges in a medium, then we can get the same force. So we can write, let above forces are equal if distance between the two charges in a medium is r dash. Let above forces are equal if distance between two charges in medium is r dash, which is less than r. Then we can write, then F vacuum is equal to F medium. So 1 by 4 pi epsilon naught Q1 Q2 by R square, F in medium K Q1 Q2 by R dash square. So that gives us R dash equal to R by root K, or R is equal to your root K times R dash. So that indicate when the force between the two charges are equal, so what could be the relation between the distance between the charges in a medium and as well as in vacuum? It means if the distance in a vacuum is your R and we want to make same force, then the distance in the medium should be your R by root K times. Same logic, same thing we are applying here. So what we are doing, although the space between the two charges is partially filled with the dielectric, so that space, that thickness of dielectric we can convert in terms of the vacuum distance. So see, if the same logic if we are applying here, then the force will be your 1 by 4 pi epsilon naught Q1 Q2 by, then already see this space and this space, it is your completely in vacuum. So that distance is nothing, R minus T. R minus T is already in vacuum and T is in a medium. T in a medium means just like here R dash in a medium. So if we want to convert into vacuum, the root K times R dash means root K times into T. So plus root K times into T. So this is called your effective distance between the two charges. So now the force between these two is given like this. So F is equal to 1 by 4 pi epsilon naught Q1 Q2 by R minus T, plus the R minus T is already in vacuum and the T thickness which was in the medium, that equivalent thickness in the vacuum become root K times into T. So net effective distance will be your R minus T plus root K into T square. So this is the force between the two charges when the space between the two charges partially filled with a dielectric. Now if in place of one dielectric, if we are having more than 1, 2, 3, 4 like this, then how to solve? Same way we can do. So if more than one dielectrics are there, more than one dielectrics are there, then force like this. Let these are the two charges Q1 and Q2, and this dielectric have dielectric constant K1, K2, and the thickness of this is your T1 and this is T2, and the distance between the two charges is your R. So first we can say effective distance. Effective distance between two charges, effective distance. So R effective directly we can say. So in terms of vacuum, effective distance between two charges in vacuum, we are converting in terms of vacuum. Okay, see, R Q1 and Q2, net distance was R, but in place between in between these two charges, there are two plates we kept here, T1 and T2 thickness. So how much distance left for vacuum? So for vacuum, R minus T1 minus T2, this is already in vacuum, plus T1 thickness in a medium. So convert in terms of vacuum. So already we have derived in the previous, just before, that distance become your root K times T. It means root K1 T1. Same as we did here. So root K1 T1. Similarly for this part, here K2 dielectric and T2 thickness, then this can be your root K2 into T2. So this total distance is your become R effective, and that distance R effective in where? In which medium? This is in a vacuum. Now force between these two we can write. So force between these two we can write simply 1 by 4 pi epsilon naught Q1 Q2 by R effective square, and substitute the value of R effective Q1 Q2 by R minus T1 plus T2 plus root K1 T1 plus root K2 T2. This is the net force between the two charges. In this manner, we can determine force between the two charges if the space between two charges are partially filled with dielectrics. Okay. Now come to the, so these are the basic fundamentals, characteristic or properties of Coulomb force and some of the application. Now we will discuss certain problem based on Coulomb force.